So do you just want us to send the PDF, or do you want the PDF and the program?
It is only PDF. So what you do, you make the program in C++. After that, you execute the program and it generates results. So you take the program as a simple ASCII file, and these results as ASCII file, put them together one after the other and convert to PDF, and that's it. What I do, I take simply in Courier font, put that in Word, then highlight the results and put them in Word, and then say save as PDF, and that's it. That's the PDF file that I have. And you do the same thing.
All right, gotcha. Thank you.
Okay, welcome. No problem. Let me see here. Uh, 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 Anthony, take off your camera if you can, please. We see you all. Bravo. Thank you very much. Speaking of this homework, there is one thing that I didn't tell you, and this is how to make the square root function, because there is the question how to make the square root function. So let me go here. Linear algorithm quadratic. It is 165. Okay, one. Okay, so in the reader, you have various algorithms that are classified according to their uh, time complexity. And of course, this starts with constant algorithms that always run in constant time. Here are examples of two of them. And the third is square root. So since square root is your homework, I would like to discuss how to make your own square root now. So the constant algorithms are exemplified by clock function. So it has a clock function here, and then clock function is taking the content of clock register, which is updated by the operating system 100 times per second. So it is updating clock variable, and clocks per second is the constant that you have in time.h library. So when you divide clock by clocks per second, you get seconds practically. And this gives you seconds as a double precision value. And this is the number of seconds from some time in the past. So if you want to compute how long does it take to execute a piece of code, you put this function seconds at the beginning, put that in some variable, and then after executing your code, take again seconds, and then subtract these 2 seconds, and you have the runtime. So this clock always works constant number of microseconds to do it. So it is not does not depend of any variable. Same as random number generator. If you have random number generator, then you have rand divided by rand max. Rand is the function that is usually in standard library.h or in namespace standard. So you have rand and rand max, which is constant. This is maximum value. So when you divide these two things, you are getting practically random number between 0 and 1. And this is what is obtained. So random number, it is big or small, always take the same time. Okay. Now, how to compute the square root? So this is your homework. To do that, we want to compute square root of a. A is a real number, and we want to compute square root of this a. So how to do that? First, I can say that this is equivalent to x squared equals a. Then let us divide left and right hand side by x. So x is a divided by x. Okay. Then we have to add x on the left and right hand side. So you have here 2x equals x plus a divided by x. And then we divide by 2 and get x equals x plus a divided by x divided by 2. Now, if you have this expression, then if x is square root of a, then a divided by square root is giving you here square root. Here is square root. You have two square roots. Divided by 2 is square root, and this is also square root. So obviously this is the same as here, but gives you the possibility to iteratively say, here is an initial value of x, and if this converges, put here new old value of x to compute new one, and then take this new to compute next one. Repeat this in iteration. Sooner or later, you are going to get that this, if it converges, it gives you square root of x, of a. So this is the method to compute square root of a, and this is the method that is implemented in each and every calculator that you buy and has square root button. So when you press square root, what's going on? Well, a couple of iterations of this formula here, which needs addition and division, or divided by 2, multiply by 0.5 if you want, but that's what you need. Just add and multiply and divide. So the formula is x equals x new equals 0.5 times x old plus a divided by x old. And this is going to eventually to give you square root. So here is your program. You can say, I'm going to compute x new as x old plus a divided by x old divided by 2. So this is the way how to compute the new value. And then you stay in this do loop as long as they are different. And you know that when x new equals x old, then that this is equal to square root, and you can display square root after that. So you have that in each iteration, you say x old equals x new, and then compute the new value of x new. And if this new value is the same as this old value, then you have it. So you repeat this a couple of times. How many times? Well, let us make experiment. So in this experiment, you can start from any initial value of a. I put here x new, I put here a. You can put here 13 if you want, will work the same way. So here is the way how you do that. I want to compute square root of 4. So in first iteration, square root of 4 will generate 2.5. Then you take 2.5 as x old and get new 2.05. Then take 2.05, you get 2.00061. Take 2.0061, you get 2. And that's the end of the story. A square root of 4 is 2. You get it here. So this one has 4 iterations. If you experiment with various numbers, it has sometimes 5, sometimes 6. But obviously, if you compute not square root of 4, but of 4,000, this is not going to take 1,000 iterations more. It is going to again do everything in few iterations. So it is usually up to 6, 7. This one is working for 4. Now, if you go to publications that show you the standard library, what are the functions inside, then they try to make this fast to execute only three iterations of this iterative procedure. But then they do first normalization, and then in order to compute this, they have some initial values that approximate square root with polynomial. So they have these 3 constants and come rather close to square root. And then after that, improve the accuracy with 3 iterations of this Newton divide and average method. So y equals 0.5 times y plus a divided by y. But they make only 3 iterations for polishing everything. And they come close to that at the very beginning with some approximation that is polynomial like this. So that's how it is done in square root function. And in homemade square root function, you can simply do it this way, and it is going to work perfectly. You are going to have 2-3 iterations more, but this is going to be done in no time. So I want you to see how this works. And I know that there are people who are seniors and don't know how to compute square root. So now all seniors will know how to compute square root so that you don't have a mystery what happens when you press on this little key that has square root on your calculator. You know what is inside. This is what is inside. Okay. So let us now go where we stopped
Wait,
last
Professor,
time.
I have a question.
Sure.
So do you want us to implement it like this, or can we use the power function to?
You do power function, I give you negative points, not 0, but negative.
Got you.
You know why? Because it is written, make your own. Your own means you did it from scratch. You don't have to do your own addition. But what means take power function? So what is your contribution? You put inside 0.5, and that's all what you invented. Square root is expression to exponent 0.5. So you take power function, put inside power 0.5 and say, this is my own contribution. Here is what I give to you. Give me the salary. Well, it doesn't work that way in this life. When you say your own, you make it from scratch. From scratch is this one here. So no power function. Let's go to the beginning.
Thank you.
Professor?
Uh-huh.
Sorry, just one quick question. If we do our algorithm, as long as it's from scratch, is it okay if it's different than this one that you gave us?
Sure, sure. But this one is the best because you have that this algorithm. If you want to derive this, I don't have time for deriving, but if you have a hyperbola, x times y equals a, this a that you want to compute square root. So imagine this hyperbola xy equals a, and the straight line, which is x equals y. So if you say xy equals a, and you have that x equals y, then you have that x squared is a, and x is square root of a. Therefore, what you get is the intersection of straight line and hyperbola. And then you go zigzag with this iterative procedure that was, by the way, invented by Isaac Newton. So you go up, down, and you come very quickly to the square root. And since this is implemented in all libraries of square root, this is by far the best way, because if there were something better, that they would put it inside. So the only thing is the difference between this piece of code here is that we have just 2 lines inside the loop. It is very short. One that is implemented in square root function. You can take a Plogger's book and you have all this code explicitly written. They have like 15 lines of code, not just 2 of them. But it is working more precisely, and it has only 3 iterations. And you will have with this sometimes 7. Okay, so they supposedly do this in a more reliable and more accurate way and faster than this iteration here. So this is the shortest program. And I think the best. I have not seen another algorithm that creates a square root in 2 lines of code. Maybe there is some, but I don't know for it. So if you do anything that you want in your own, it is perfectly okay. It is perfectly okay, no problem. But I just want to stop trying to solve all problems by taking somebody else's solution and putting inside two numbers.
Okay.
I'm simply trying to eliminate this approach to life. Okay. The approach has to be, if I can solve it myself, I'll solve it myself now. If I cannot find the solution, then I go and dig for somebody else's solution or read a book or do something else. But not that the first instinct is I'm collecting things from internet, from libraries, from everywhere without thinking and putting inside my little number, and then that's the solution. We are trying to develop a skill of making the library. Power function is a tool. I understand that. And we use tools. But there are people who make tools. Let us be tool makers if we can. And this is what we try to develop. That's the philosophy.
Okay. Thank you. Okay.
Okay, so let's try to be tool makers. That is the idea. Now, we
Professor, I have
have...
a question.
Go ahead.
So, Professor, for the first, second, and the third question, it is mentioned that we have to use the 8-bit integer format. So, is it okay if we use the normal integer?
Integer for these initial questions that you are asking.
Yeah.
Let me tell you, I suggest that you used signed characters. Everything that is bigger than that gives you big numbers. If you take just 8 bits, then you know that number is going from minus 128 to plus 127. And you can control everything by heart. So that's how I did it, and I think that this is the simplest. You can do, of course, with short integers or with integers, but then you have this 2 billion, and it is more difficult to see these errors. So if you have unsigned integer to deal with, take it in unsigned byte, unsigned character variable, and then you have from 0 to 255. You add, for example, 200 plus 200, you are not going to get 400, but it is going to go from 0, and you will get some number that is less than that. So it is much easier to do it with short than with long numbers, and the result is the same. You have to demonstrate these numerical problems, and you demonstrate them in that way. Is that acceptable?
Yes,
Is that what you wanted to hear or something else?
Yes, Professor. And for the maximum number limit, we can take the C limit, right?
What maximum number? Can you speak a little slower, because I don't hear very well, so that I can understand the question. Could you repeat it, but slowly, please?
So for the maximum number which we are taking, maximum integer number, so that can be the C limit, right?
Well, the maximum integer number is 2 to n minus 1 in the case of unsigned numbers, or 2 to n minus 1 in the case of signed numbers. So this number is known in advance. You know what is the largest number, so there is no mystery about that.
Right.
So you are not taking it; it is given. So, for example, if I have signed signed number integer, okay, what is the largest integer in in the case of single byte? It is 127. So I put 127 plus 2. 127 is legitimate number. 2 is also legitimate number. What is the result? You jump from 127 first to minus 128, and then to minus 127. So the result 127 plus 2 equals minus 127. This is wrong, and this is what you have to show. So I would simply put unsigned signed character is 127 plus 2, and then take integer of that, display it, and you are going to get minus 127. So 127 plus 2 equals minus 127. Is it wrong? Yes, it is wrong. Is it demonstrating the overflow? Yes, it is demonstrating the overflow. Is it something that you can easily control without any calculation? Yes. It is simple. It is correct. I will put it that way. You don't need anything more. But if you want, the same situation will happen if you take integers. But then you are going to have that the largest value is going to be 4 billion. Okay, so 4 billion plus 2 is going to be minus 4 billion something. Okay, but it is exactly the same phenomenon. It is much more easier to see it with small numbers than with huge numbers. That's what I'm trying to tell. Is that okay?
Yes, Professor. Thank you.
Okay, thank you. So last time we were here on this slide here. So we were speaking about classification of loops, and we said we have loops with conditional exit, like while loop, loops with counter, for example, like for each element in n do body through set elements, and we have also loops with counter and conditions. So for each element in set where condition is satisfied, perform this body, or loop with step. So from A to Z with step S, do where condition is satisfied, do body. So these are loops with condition. They exist, of course, in SQL in a more complex construct, but usually people, normal languages don't have that. Normal languages have loop with the exit at the top, loop with the exit at the bottom. So these are standard, not say normal. There are no normal and abnormal languages, but there are languages that are procedural, like C, C++, and procedural part of Java, procedural part of Python, procedural part of C# and Ruby, and all of them have procedural programming. So they give you loops. Loop can be loop with the exit at the top, can be loop with the exit at the bottom. That means exit at the top means that you can skip execution of this block here if you want. And here you must always execute this block at least once. And then you go out if you have condition for exit. You have exit in the middle. Do first part of the loop, and then you can exit after that or continue another iteration. So you have first part and second part, exit in the middle. You can also have multiple exits. So you have this exit and any number of them. This is not considered particularly good practice, and try to avoid, because all these exits can be merged together in one, becomes a little more readable. But if it is algorithmically simple and semantically understandable, then you can have any number of exits. This is also acceptable construct. But it has to have one input point and one exit point. That's important. Whenever you get a new language, you have to know whether this condition is condition for staying in the loop or condition for exit from the loop. That's what you always have to ask. And of course, the answer is that if you have C or C++ or Java, they have always condition for staying in the loop. So when you have do loop, you say do this while condition for staying in the loop is true. So you loop through this multiple times. Now, what is the simplest possible design of the loop? This one that is used from EDA. EDA is a language that was developed for military purposes as object-oriented algorithmic language to be used in development of military software. So EDA has this loop, loop and loop. And this is infinite loop. So whenever you reach end loop, you go to beginning and you move through this. And then has beautiful construct, exit when condition. So this is the exit that you can put at the top or at the bottom or in the middle, or you can have more than one of them. So since this is sliding up and down, it works as the loop with the exit at the top, loop with the exit at the bottom, and loop with the exit in the middle, and loop with multiple exits. So all this is done with one simple design. So you don't need to have while, do while, repeat until, and blah, 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 other things, because everything is built in this simple loop. So this is beautiful, the simplest possible. And unfortunately, we have that only in Ada. There is something similar in Ruby also. But we don't have that in C or in C++. You have to put infinite loop, and you can say if condition, then break. So this would be something that is equivalent. But people use while loop and do while loop instead. Then loop with general update is one that we most frequently use. This is called for loop in C, C++, Java. For initialization, and then you have condition for staying in the loop, and then you have update at the end of the loop, and you have body that is here in the middle. So there is no such a thing as for loop. Compiler immediately transforms that into while loop. So what is inside is this. You have initialization that comes first. Then while condition is satisfied, we perform body. And after that, we perform update. And after this update, we go back to condition. So here we were speaking about this loop general update that has body and update. So don't do things like this. It is not particularly good practice. So make it just the standard way, and this is okay. Now, if we try to see what is the most general way of making such a loop. So for loop, initialization, test, update, body has here initialization, test, body, and update. So this is 1, 2, 3, 4 destinations of job. So the most general thing that you can do is to have jumps to all of them. So if you have body, you can say break. Break is jump to the next statement. Okay. You sometimes want to have jump to update, to skip the rest of the body. And this is called usually continue or next, if you want. So next is bringing you to update. Redo, if you have it, is jump to the beginning of the body. So you tell your customer, okay, take now and in this program, give me some input data. You get some input data that are questionable, come to this position here, and you see that you cannot create result. And then tell a user, hey, give me something else, this doesn't work. So you want to, in the same iteration, you want to go to the beginning of body. So this is redo. And the worst case scenario is that the whole loop is in catastrophic condition. You have to repeat everything without breaking the program. This is retry. Retry is jumping to initialization. So if you have break, next, redo, retry, there is nothing more that can be done. So this is the most advanced and the most elaborate form of for loop. And this you have in Ruby, for example. You have here loop and then loop and end. So this is going from here to the end, similar to Ada. Loop, do, and end. And then what I do inside, I have I, which I use as counter with 0, increment by 2 in each iteration. So 0, 2, 4, 6, 8, 10, etc. Break if I is greater than 10, and then put string I, so display I. So what I get is 2, 4, 6, 8, 10. After then you get 12. 12 is greater than 10. And we jump to next statement, which is this put string, which is this space that I have here. However, if I want to show next, then I have the same loop, do end, and then I have the counter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if I is greater than 3 and less than 7, that means 4, 5, and 6, I want to skip this here. So what I have next inside, or continue if you want, 1, 2, 3, and then 4, 5, and 6 is skipped, and then 7, 8, 9, 10. So you can go this way. So this is the way how the loops work in all languages. One particularly nice and frequently used type of loop is loop with implicit counter, if you have it. So you want to execute this block 50 times. So you say perform block 50 times. You don't want to define the counter. You don't want to instantiate the counter. You don't want to increment the counter, and you don't want to test the counter. Somebody else will do that for you. So you perform block n times, and of course, this is the way how to perform block. So perform block n times. In call, you have this construct, but it is important to have this construct combine with function call. So what they have is a very nice construct is this. You have a piece of code that has the label loop. Loop means this is the piece of code between this loop label and some other label. Therefore, this is a kind of function. And when you say perform loop 50 times, it is going to jump with this perform to this loop, execute loop, come back here. And then execute it next time and next time and next time 50 times. And after that, we'll continue this program here. So the idea of this body here is that you can say perform loop without these n times. In that case, it is going to jump to this function, execute function, and come back. Okay? So this is function call, like in all other languages. But you can combine function call with loop that has n times. You can also say compute this, perform this varying specific variable from initial value to some final value with some specific step. Well, if you do it that way, this is going to be more complex and still rather simple, that combines function call and loop in a single construct. Very nice thing. Loop with explicit counter is something that is frequently used. If you don't have it, then you instantiate your own counter and count in that way. There are loops with counter and condition in some advanced languages, SQL, etc. So if you have for loop where condition is satisfied, so this is combination of for loop and if statement inside. And then you have that for this, in the case of this situation, you have that you can find the maximum value in a single line. So this is a Pascal version with where for you take first the first component, put this in I maximum, and then go from second component to the last one. And if A of I is greater of maximum, you say maximum is A of I. And if this is not the case, then repeat again. And when you go out, you find maximum in a single line. You can do the sort program in 2 lines also. So you can say, if I want to sort array of components, then one inefficient O of n square sort is the usual select sort. So you have I that is going from 1 through n minus 1, and j is going from I plus 1 to n. So you combine 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 components, and always put the largest or the smallest at the beginning. And then when you finish this iteration, increment I to 2, and then you have to combine 2, 3, 2, 4, 2, 5, 2, 6, etc. Of course, this gives you quadratic algorithm, but you can write sort in 2 lines. So you have that where A of j is less than A of I, then you swap this and put the smallest value at the beginning. So you have an increasing sort if you do it this way. So you can write it in 2 lines if you have this where. If you don't have it, you just put if statement and everything is okay, no problem. So let us now consider one important theoretical problem. Imagine that Bill Gates comes to you and gives you $30 million and say, make a new language for me. So you take this 30 million and go home and start thinking how to make a new language. What are the questions that you have to answer? First of all, what kind of paradigm you are going to implement? Are you going to be strictly procedural or logic or functional or object-oriented or multi-paradigm so that you have more than one paradigm supported? So this is the first question to ask. But there are going to be other questions that you have to answer also when you design the new language. So how to design specific language? What data type to implement? Are you going to have integers and everything else, or you are just going to have numbers and somebody will take care, are they integers or real or something like that? For example, for children, it is not advisable to have something that is integer or real. These are all numbers, so okay, we work with numbers. Or you can have something else. Or what data structures, control structures to implement? Well, I would like now to focus on this question. What are the necessary control structures? This question is answered by answering is more better or less is better, big or small. So the question is, what components are absolutely needed? What is the minimum number of components that you can have in order to design software? What is the minimum number of control structures that you have to have? Okay, well, there is the answer to that question. The answer to that question is given for so-called proper program. Proper program is program that has one entry point and one exit point, and no infinite loops and no unreachable code. So you have here entry point, single entry point, and single exit point. And this proper program is this big potato here that has statements inside, like this one. And for each statement, you can go, there is a path going from entry point through that statement to the exit point. So you don't enter here and do infinite loop that never exits down. And you don't have unreachable code. For example, you have piece of code that you cannot reach. So these are irregularities, both infinite loops and unreachable code. I want also to show you example of infinite loop and unreachable code. And imagine that you have computer that has accumulator. So load A means take from memory location A and put in accumulator this value. Then add to accumulator something from B. Then perform some load body and then jump to this start. So jump to start and have here loop that repeats forever. So this is an infinite loop. You jump from here. What happens after this jump? If you have this multiply C and store D, this is unreachable code. You can have it in assembly language programs when people modify the program and have unreachable code that remains inside because there is no way how to come here, because before that is a jump statement. So the rule that is general rule in programming, after jump, there must be a label. You must have here to have label if you want to reach this code, because you have to jump to this label. On the other hand, jump statement should never have a label, because if you put label to jump statement, that means this is destination of another jump. So if you jump to jump, why to jump when you have go immediately from the beginning to the final destination? So the rule is jump statement should never have a label, and after jump statement, there must always be a label. So like this, you have jump without label, and after that, multiply with label. So this is unreachable code. This here is infinite loop. So if we don't have that, we have proper program. Proper program has the theorem that is developed by Giuseppe Jacopini in 1966 called structure theorem. It says that each proper program can be composed using loop with conditional exit, sequence, and auxiliary variables or flags, and nothing more. This has profound ethical consequences because it tells you that whole software can be developed using only while loop and nothing more. You have while loop, you can develop any program that you want to develop. Of course, you have to have the possibility to define variables and to have a sequence. But there is no need for if then else, which looks surprising to some people because they think that if then else is something that you cannot live without. But no, you don't need it. The only thing that is necessary is the while loop. So let us see how this works and how to make, therefore, the while if then else with while loop. Because if you don't need if then else, that means that it is possible to make if then else with while loop. So here is how to do it. Imagine that we have C++ version and we say if condition, and then you have a block that is called then part, else, we have else part, semicolon. So this is the end of this statement. So how to do if condition then part else this part without if statement. So the first thing that I'm going to do, I'm going to compute this condition and put it in variable C. This is the flag. This is auxiliary variable. And I will take its negation, not C in this C. So I have condition and not condition. These two flags. Then I have while loop, while condition is satisfied. So if condition is true, I'm going to enter this block and execute then part. Then this loop will try to execute then part for the second time. But I'm going immediately to close the door and will say C is 0. So when I put C is 0, that means it is false. When you try to execute this for the second time, this is going to be false, and you drop to the next loop. If C was true, this is going to be false. You are not going to execute this second loop. Therefore, if condition is true, we execute then part only once and go out. If condition is false, then not C is going to be true. We come here with false, skip the first loop, come here with non-C is true, execute else part. Then close the switch by putting non-C is 0, come here, try to execute the second time, fail, go out. So if C is true, we execute then part. If C is false, we execute else part. So this is if then else is made by using this construct here, and it is working in a simple way. Therefore, you don't need if then else. Sometimes you have that structure theorem is given in the following way, that say each proper program can be composed using the following three components: loop with conditional exits, sequence, and branching if then else. If then else is not necessary, but if you have it, it is not going to hurt. Okay, but theoretically, the only thing that you need is while do. While do or do while, whatever you want. You have to have loop with the exit at the top or at bottom, but you have to have loop with conditional exit. There is something similar in hardware. In hardware, there is Charles Peirce theorem that says that the logic operation NAND and the logic operation NOR are each individually sufficient to derive all other Boolean operations. That was proved in the end of 19th century. And indeed, if you have NOR operation, then negation can be not as P nor P. P and Q is made in this way, and so on and so forth, implication in this way. You can easily prove that in a second. So this has, again, profound consequences, because NOR gate is one single transistor that has one resistor in collector, base, and in emitter has also one resistor. And you have that with this single transistor that has multiple inputs, several resistors, and the input to base of transistor, you have that you can make all these logic operations. So you can build the whole computer using only NOR gate. So if you know how to put MPN or PMP layers one on top of the other, you can build all hardware on top of that. And this is what we use in VLSI design. And therefore, this has very important practical consequences. So Peirce theorem tells you that all hardware can be made with NOR gate. And Jacopini theorem tells you that all software can be made with while loop. Of course, we are not building all hardware only from NOR gate and all software only from while loop. But theoretically, it is important to know that this possibility does exist. And for example, that means that you can make all do while using while do. How to do that? Well, if you have do body while condition, first you execute body, and while condition is satisfied, you repeat body again. So this is equivalent, but body is repeated twice. So you assume, of course, that this is a function that is called twice. If body has 2000 lines of code, you have that as a single function, and then you call it twice. So you don't repeat this body twice. But this gives you logically the same behavior as do body while condition. The same situation is if you have loop with the exit in the middle. You can make it using either do while or while do. For example, if you use do while, you enter in do loop, execute this block A, and then compute flag, which is not condition. So if condition is true, this is exit, and this is flag is condition for staying in the loop. So condition for staying in the loop, if it is satisfied, execute B. And they stay in the loop while flag go to B, to A. Now the question is, why not to put a condition here? Well, because of this B. B can modify this condition. If condition is that X is 0 and this flag is incrementing this X, then this B is incrementing this X, then this flag will save you to memorize what was the condition at the moment when you had to exit. So you have to have this flag. You cannot do without it. But if you have, for example, while do, you can simply execute A first, and then while not condition, you perform BA, 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 etc. And this is going to work without flags. So you can always modify one control structure and transform it to another control structure. So all software can be written using the while do loop, and all hardware can be made using NAND or NOR gates. So theoretically, this is important because it tells you that the whole building of software and hardware and all complex systems are always made of simple components. There is always brick that you use to develop a wall. So you have to have brick, but then brick on top of brick on top of brick, you make a wall. And then after that, you take 4 walls and you make a room. And you take several rooms and you make an apartment. And then you put one apartment on top of the other and you make a building. And then you take multiple buildings and make a street. And take multiple streets and make the city. And so we are always having components that are used to make more complex systems. Systems are made of components, interconnected in some way. So it is extremely important to know what is the basic brick, how to start that, And the start is theoretically while do loop in software and NOR or NAND gate in hardware. And this is why we have to know that. The next thing that is important topic are expressions. What are expressions? Well, expressions are combinations of operands and operators that return a value. That's important thing, that they return a value. So all language constructs can be interpreted as expressions. So let us take the if statement. If statement is an expression if it returns a value. But in many languages, like in C, C++, Java, if statement is not returning a value. It is doing only side effects. If condition is satisfied, perform then part. Otherwise, perform else part. And these are two possibilities, and each of them is creating the side effects, nothing else. So the question is an assignment and if statement and all other statements, are they expressions or not? If they're expressions, they return values. So there are expressions that are illegal. For example, for each operator, you have rules what can be on the left-hand side, what can be on the right-hand side. So if you have division, division in all languages is defined, you are going to divide numerical objects. You have to have here a number, and on the right-hand side also a number. And if you have number and number, you are going to divide them and get the result. If you have number combined with string, this is going to be illegal. You cannot divide 3.14 by string. This is not going to work because this is not the way how this operator is defined. Therefore, you have that you can have mixed mode expressions, and if they are done with different data types, then we automatically promote simpler data types to those that are more complex and perform operations with the same kind of data type. Now, examples of side effects are, for example, this expression here. What I'm doing here, I'm computing the value of x. But before that, I want to decrement this n. After that, I want to increment this k. And at the same time, I want to assign 3 to p. So assignment of 3 to p is a side effect. Incrementing k is side effect. And decrementing n is side effect. But you can write it in this way. You first decrement n, and then add 1 to that. Then you compute 2 plus k, and then after that increment k. And then assign 3 to p, and then multiply these three things and put the result in x. So side effects are not always safe. Generally, they increase program complexity, should be carefully controlled, and if possible, they should be avoided. Try to avoid writing program in this way because it adds complexity. It is much easier to say n minus minus before you go here and then perform this and say k plus plus after that. It is going to be more readable than this line here. So take this into account. Another thing is that assignments in some languages are expressions. In some languages, assignments are not expressions. So let me show what are the consequences of that. And in all languages, if you have a new language, you can always ask, is assignment an expression or not? For example, Fortran 77 has that assignment is not expression. So you cannot write A equals B equals C equals D equals Z in Fortran 77. This is not going to work. You have to say A equals 0 in next line, B equals 0, C equals 0, and D equals 0. These are 4 different statements. And in C++, This is not the case. You can do it in this way. It's right associative. 0 is put in D, then this returns the value 0, then this 0 is put in C, and so on and so forth. So it is also possible to do things like this. You say A is 271 times B plus C. So first multiply 271 by B, add C to that, return the value from this expression, whatever is the result, put that in A. And then this parenthesis is returning this value. And this value is then multiplied by 3.14, and the result is stored in X. And then this whole expression is returning X, which nobody uses. So you can use it if you want. So if I say, for example, C out, insert this expression. And this expression is first going to add 3 plus 4 and put that in 7, in N. So N equals 7. And this 7 is going to be returned from this pair of parentheses. Then we are going to multiply 3 times 7, and we get 21. And 21 is going to be inserted in output stream. Okay? And then after that, you are going to get 21 on your screen, and N is going to be 7 to be used in your program. So if you have assignment, which is an expression, then both A equals 3 and A assigned 3 are legal statements. Therefore, be careful that if you type 2 quickly, that you can forget to put the second equality, and then you are going to have this assignment. If you have this assignment, 3 is assigned to A, and since assignment is an expression, this is going to return 3. 3 is considered non-zero. Non-zero is true. So if true perform statement, it is always going to execute this statement. And this is, of course, legal, but it is dangerous. Good compilers are going to say, hey, you have here an assignment. Are you sure that you want to do that? Because it assumes that you would like to do something like this. That's what some compilers will do. Some other compilers will say, hey, you are writing program in C. C is language for professionals. If you are a professional, you know what you are doing. Therefore, I'm not going to tell you anything. If you want to have A equals 3, I'll give you A equals 3, and everything will be okay. So this is another approach to making compiler. It is also legal to do it that way. So what we have as a consequence is that we can have standalone expressions. Expression like 7 is legal in C++. X, written like this, legal in C++. A plus B, legal in C++. All three of them do nothing, and compiler simply ignores them. But it is not an error. So you have A, you have B. You add A plus B and get the result. This result is used by nobody. That is legitimate. Compiler will say, okay, I'm going to compute this, but will not use. Or will simply kick out these statements because optimizer will say they have no any purpose, therefore take them out. But this is legitimate way. It is very good if you have that stance can be interpreted as expressions and they return the value. If you have this kind of statements, it is good to have the beginning and end. So if you have if condition then z and if, you know where is the beginning and where is the end. And so this here is an expression. Now, this expression in some languages is executed for side effects, returns nothing. In some languages, it returns the value. So the case from Ruby is where if returns a value. So you have if statement, which is an expression that returns the value. If x is 1, then if will retain string 1. Else, if x is 2, then it is going to return string 2. If it is 4, string 4. If it is not 1 or 2 or 3 and 4, it is going to return many. So this if statement from if to end. So this is if and end in Ruby. And you return either 1 or 2 or 3 or 4 or many. It returns always a string. And this value that is returned is assigned to name, which is the variable name, which has no any data type. This is dynamically typed language where variables have name that is completely different from the value. So you can have here name equals 3.14. Then after that, name is string. And then after that, name is 15, if you want. And all this is legal. So if statement is an expression, and this expression returns a value, and this value is given to this name, and name becomes a string variable after that. So you don't know what is the variable type until you assign the value. When you assign the value, you know what is the result. Okay. The same is with case. When x is 1, return 1. When x is 2, return 2. When x is 4, return 4. Else, return many. And again, case is an expression that returns a value. In this case, a string. And then you assign this string to this variable name. So this is dynamic assignment of value. And then after that, you can use that any way you want. So for all expression, we have to specify arity, type of operands, associativity. You can have parentheses, free notation, priority, etc. However, I want to show you also something that is important with expressions, and we are going to come back here. And this is the order of executing expressions. Something that is very, very dangerous is to assume the order of evaluation. Most languages tell you nothing about the order of evaluation of operators, operands. Why not? Because this gives an opportunity to compiler to perform some optimizations, to do something optimally. So compiler has the freedom to do that. And so if you have expression like y equals f plus g plus h, you know that you are going to add this value first plus this value and then plus h value. But that does not mean that f is going to be computed first, g is going to be computed second, and h is going to be computed third. That is not given to you. It is not promised to you. But if you have computed f, g, and h in some unspecified order, then the addition of this is going to be first f plus g, and then result plus h. But that does not mean that they are evaluated functions, first f, then g, then h. If you don't promise that, then compiler can optimize and do that in some optimum way. So in the case of C language, they don't suggest to write a of n is n plus plus, because you are not sure is this n plus plus affect this n or not. It is better to write, this is not safe. So because some compilers can interpret that in the wrong way, to first compute n plus plus and then to perform this n, because you cannot do assignment unless you finish this. So how are you going to finish this? By saying n and then putting a of n, or you're going to compute n plus plus and then put n plus plus inside. So this is not clear. And therefore, don't do it. That's the message. It looks simple, but it is unsafe. Say a of n equals n, and then put n plus plus, and no doubt about that. This is perfectly okay, works the way you expect. So good practice is order independent code. Don't write things like x is a function of g of n and h of plus plus n, because if you do this, you don't know what is going to be performed first. For example, what kind of n is this one here? Is this original n or n that is already incremented? If you have here plus plus n, you are going to have incremented n, and you have that this is not original n, but incremented n. So this should be written as compute function of g of n and h of n plus 1, and then increment n. And then it is safe. There is no question about that. If you don't believe that, I'll give you an example. An example is this one here. I have a function. Function f of n is returning n. So it is doing nothing. Function f of 1 is returning 1. F of 2 is returning 2. Okay? So here we go in this program. I put n equals 2. What is returned by this function? F of 2 is returning 2. So this is going to display 2. Then after that, the same thing repeats. I again display 2. Then I increment this to 1, 2, 3. So it is 2, 2, 3. And then here should be 3, and here should be 2, because it is decremented. So it is 2, 2, 3, 3, 2. What is displayed? 2, 2, 2, 1, 1. It is not 2, 2, 3, 3, 2, as I would expect, because this is displayed first this, second this, third this, fourth this, fifth this. So what I discover here, that the function computation order is right to left, not left to right. Why is that so? Because the compiler thinks that this is the best way to do things and optimizes something. So you have that first we perform this operation. So since n is 2, then you have that this is decremented to 1. This here is 1. This here is 2, 2, and 2. Now when you have this 2, 2, 2, 1, 1, then you insert them in output stream in a proper order with associativity left to right. So you get 2, 2, 2, 1, 1. What remains here at the end of this statement? You have that n is this last expression, which is 2. So you expect here to have 2, 2, 3, 3, 3. So 2, 2, 2, 2, 2, 3, 3, 3. But you get 3, 3, 3, 3, 2, 2, which is obviously not what we expect. But if you go right to left, you see that it's going systematically right to left. So finish this with 2, and then here it has 2, 2, 3, 3, 3. Here we go, 2, 2, 3, 3, 3. So you finish this with 3. You go here, 3, 4, 5, 6, 7. You have 3, 4, 5, 6, 7 in opposite order. So what this program is doing is computing things, evaluating functions right to left, not left to right. So you go home, write this for your computer or for any language that you have and you use, and see what you're going to get. Are you going to get this evaluated left to right or right to left? This here is the dev C++ compiler. So this is respectable compiler that is developed by GNU, that is optimized gazillion of times. And I use this for producing all my commercial software. And it is good compiler, never made anything stupid to me. But you don't have to do things like this, because this is not part of C++ language. It is not telling you that these functions are going to be evaluated left to right. This is not written. This is not promised to you. It is promised only that these values are going to be inserted inside output stream left to right, but not that computation of values is going to be done left to right. Therefore, this is done intentionally in order to do compiler optimizations and try to write code that is order independent. So that in whichever order you go, there is always the same result. So all this incrementing perform outside of this cout statement. And then you are sure that everything will work correct. Okay. Because for some other language, it is going to go left to right. For some other language, maybe it is going in random order. You never know. Therefore, and for other compilers. So if you have different C++ compilers, try to this on different compilers to see what will happen. Try to run this on your compiler to see, is it going to give you this, what dev is giving to me. This is dev compiler, it is free. You can download that from internet, install on your machines, and it works very nice. It has all classes that are displayed. It has graphical user interface. It has possibility to memorize all previous objects that you use. And it is very nice advanced compiler, good for doing professional software. But again, if you don't know how to use it, you can get things like that. So this is why we speak about expressions, because we need to know what is the order of executing them, and this order is, in this case, not defined. It can come in arbitrary order. And when you come to scheme and racket, you are going to see expressions that are executed in arbitrary order. The loop that is done in scheme, Lisp, and racket is done with updates in arbitrary order. If you have multiple indices, they are updated in arbitrary order. And this all is that with intention that it can serve some other purposes. So this is all what I have for today. Is there any question about this or something else? Okay, so we can stop here. And we'll go a little bit back next time. But I wanted you to see this because if you do these experiments for your homework, it is better to know these things up front and not to be surprised. Okay. No questions.